So for the multiplication rule, what we're looking at are cases where we want one thing to happen and another. And the way this behaves is essentially the same way as the fundamental counting principle for counting cases, except now we're adding in the layer of complexity that we're doing this with events and probabilities instead of just numbers of things. But if we want the probability of some event A and another event B, if we have that A and B are independent, then the probability of both of those happening either simultaneously or one directly after the next is just the probability of A times the probability of B. And to understand this, we're going to look at a couple of quick examples. So here, for this first one, we're going to go back to one of those cases we had in the last example. We are going to find the probability of tossing a coin and getting heads.
Call it. Call it, yes.
And then rolling a die and getting a 6. Well, since we saw in that last example that for these events A and B, we had that they were independent. If we want to find the probability of getting a head and getting a 6, it's just the probability of getting a head times the probability of getting a 6. Where here, that would just be 1/2 for the head times 1/6 for the 6, for a total probability of 1/12, or if you prefer a fraction, 0.83.
Well done.
So it's a little bit in terms of notation and all this naming stuff that makes it seem like it's going to be pretty intense, but the truth is, it's really not that bad. On the other hand, let's say that for interior cruciate ligament, that is ACL reconstructive surgery, the observed probability that a surgery is successful is 0.95, 95%. Find the probability that 3 consecutive surgeries are successful. Here, we're going to make a bit of an assumption. It might be a fair assumption, it might not be, but for us, if we want to find the probability of A and B and C, we're going to assume that these 3 things are independent. It might be a little much to assume independence in this case, because what we have are human beings, where if one person is performing all 3 of these surgeries, they might get more or less confident as they're going, they might get more or less tired as they're going.
I know I'm supposed to cut something, but what? And where?
But for the sake of simplicity, we are going to assume that these are all independent from each other. If you get far in statistics, you'll see the words independent identically distributed, which is the sort of thing that's going on here. But the idea is that if we want all 3, well, really, that's the same as the probability of 1 success taken 3 times, or numbers, 0.95 times 0.95 times 0.95. So even adding a third case with independence, we still do essentially the same thing, we just have 3 of them. And as a result, this probability here would end up being 0.857, or if you prefer to think about that as a percentage, about 86%. So 3 in a row is pretty good odds. On the other hand, if for some reason we want to know what the probability is of getting at least 1 failure, say you want to get a sense of how bad it could be.
The knee bone's connected to the something. The something's connected to the red thing. The red thing's connected to my wristwatch. Uh-oh.
We can understand that that is, in essence, the complement of this. That is, if we want at least one failure, that's the opposite of everything succeeding. That is, it's the opposite of no failures. So we can think of at least one failure as 1 minus the probability of 3 being successful, because 3 successes is the same as none failing. Which here would mean the probability we want is just 1 minus 0.857, or 0.143. So there's about a 14% chance of getting at least one failure out of 3. It's still pretty good as far as probability goes for a major surgery. But that's the idea here that we're seeing is at least one failure could be read as 1 or 2 or 3, which means you have a few different cases to consider that all involve a bit of work that we haven't gotten to yet. Or we could just use the complement and get there quicker. And the last thing we're going to see in this chapter is essentially the other side of the coin, because we made the assumption about what happens for independent events. That means we've got to see what happens for dependent events.